So today I'm going to go over some basic rules, some algebraic rules of properties that we need to develop something down the road, because we know that a derivative on day one, derivatives were the slope of a tangent line of a curve. But now that we've been doing derivatives for a while, I mean, we did derivatives to figure out how many apple trees to plant to maximize production. We did a derivative to figure out how much to charge for a room in a hotel. In other words, there was no graph, there was no tangent line. A derivative is actually an instantaneous rate of change. If it's a graph, then it's the tangent line at a specific point, but we're way beyond graphs. We're infinitely further and more advanced than just something as simple as graphing. Well, it turns out the first application of integrals, most people know, is just to find area under a curve. But it goes way beyond areas. We can find volumes and arc lengths and surface areas and all sorts of things. So in order to do this, I'm going to review some stuff that you may never have seen before involving what are called summations. So this notation, this is called a capital sigma. And if I said I want to do I equals 1 to, let's say, 1 to 5 of A sub I, and that's how we actually say it. I is called the index. The capital sigma means I'm going to add up my terms. My first one's going to be 1, my last one's going to be 5, and I increment by 1. So that means that this would equal A1 plus A2 plus A3 plus A4 plus A5, whatever those values are. I'd usually have a general formula. So for example, if I said, let's add from 1 to 4, and we'll add 2i plus 3. Okay, that's my AI, if you will. So I start by putting I equal 1. Okay, so 2 times 1 plus 3. Now I put it I equal 2. 2 times 2 plus 3. Then 2 times 3 plus 3. And finally, 2 times 4 plus 3. So this statement here is equivalent to this. Now, one of the reasons we like summations, if I have a general formula, we like summations because if I had to add up 1,000 terms, I just write to 1,000. I don't need to physically write out the terms. If I wanted to do this by hand with a calculator, that's fine. If I wanted to use a computer, anybody who's ever done any programming with the computer, this is what's called a do loop. I mean, you guys remember doing a do loop for I equal 1 to 1,000 do. That's quite literally day one of any programming class. It's so basic. So programming something to do a summation for you is absolutely trivial. We're not worried about that. That's a really easy thing as long as I have the general term here. So this is what a summation is. So why do we need to know this? Well, we're going to be doing the algebra of summations today. So I'm going to create a couple of really important formulas. So, and we use generic terms like the AIs. That just refers to a set of numbers. So consider the following, that I have the sum from I equal 1 to n of AI, and I'm going to add it to the sum of I equal 1 to n of BI. So these guys might be, I squareds, and these guys might be the cosine of I, it's whatever you want it to be. It's just some general expression. I'd like to know if I can combine these two. Okay, so let's write it out. So in the first case, it's going to be A1 plus A2 all the way up to AN. So that's a simple way of describing this. The second one's going to be B1 plus B2 all the way up to Bn. So I have two finite sets of sums, and I just want to add them together now. So it's a fairly simple thing, but these are real numbers. And we know real number addition is both commutative and associative, meaning I can rearrange and I can regroup. So I could write this like this. A1 plus B1 plus A2 plus B2 plus all the way up to AN plus BN. So I just applied a little bit of algebra to this. Well, why is that important? Because this is the sum from I equal 1 to n of AI plus BI. We've just proved that the sum of the summations is the summation of the sum. Does that sound familiar? Sum of the limits is the limit of the sum. Sum of the derivatives is the derivative of the sum. We have a sum property. Now we know the product of derivatives is not the derivative of the product. We know that. We know there are limit properties that don't apply to anything else, but there are two major limit properties that do extend in other areas. And that is the limit of a sum is the sum of the limits, and the limit of a scalar multiple is the scalar multiple of the limits. We know those apply to derivatives. Do they both apply to sums? Well, I've just proved the sum of a sum, yes. Now let's do a scalar multiple of a sum. So let's go back to here. And now what I want is, what if I had, let me write this way. K is an arbitrary constant, but it's the same constant throughout. So now I want to know, I have the summation of a constant times my term. Well, if I expand this, this would be KA1 plus KA2 plus all the way to KAN. But clearly, since every term has a K in it, I can factor out the K. And this would become K times A1 plus A2 plus all the way to AN. But that's K times the sum from I equal 1 to N of the AIs. And there we have it. That limit property and that derivative property, the sum of a scalar times function is a scalar times the sum. I can factor scalars out of a summation. In other words, we just did. So those are two very, very powerful properties that we're going to use in a moment. So the algebra of summations is actually not very complicated. Most of the time when you're dealing with summations, you're just given a summation and you add it up and you give a numerical answer. That's very, very nice, but that's not very interesting. So we're going to look at a very simple formula next that some of you may or may not be aware of. It's one of my favorite legends, by the way. Okay, Carl Friedrich Gauss. He's my favorite mathematician. Okay, he's not only one of the guys who invented calculus, he's also probably the most important contributor to linear algebra, which is another one of my passions that I teach and develop and derive stuff for linear algebra. Anybody who's ever worked with a matrix before and you did matrix operations, they usually refer to that as Gaussian elimination. Some of you may have heard that term. So Carl Friedrich Gauss, who lived, a couple hundred years ago, smart guy, but apparently, as the story goes, again, it's a legend, so it doesn't matter if it's true or not. He was kind of an obnoxious little snot as a kid. And so he's in the one-room schoolhouse, which is how it typically worked. All the ages were together and they all had their little easels, basically little chalkboards and their, pieces of slate, granite, kind of acting like chalk. People say, why didn't they have pens and paper? Because there wasn't pens and paper 200 years ago. you couldn't go down and just buy a ream of paper and pens. It did, there was papyrus and things like that, and newspapers came along a little bit later, but no, there wasn't the ability to just write pencil and paper. So as the story goes, one particular day, little Carl Friedrich was being particularly obnoxious in school, and so the teacher says to him, all right, go add up the first, million positive integers, add up 1 plus 2 plus 3 plus 4 up to 1,000,000, figuring that'll keep the kid busy. So of course he comes back a few minutes later with an answer. Of course the teacher doesn't know what the answer is because this kid is like off the charts genius. And did he just add up 1,000,000 integers in his head really quickly? Probably not, because like any good mathematician, he has the one most important characteristic that you have to have if you're good at math, and that is laziness. You see, a lazy person always looks for an easy way out. They look for a shortcut. They got to get the job done. They got to get it done correctly, but they don't want to work in labor. If a problem can be done in 2 steps, why would you take 10? So what he did was something like this. He says like a 1 plus 2 plus 3, and then at the other end, I got 9, 9, 9, 9, 9, 9, and then I got 1,000,000. All right, I got to add up all these numbers. Okay. Well, that's a lot of numbers. So what if, just for the heck of it, I wrote the same numbers in reverse? Well, we all agree that if I add up 1, 2, 3, 4, 5 up to 1,000,000, and then I go 1,000,000 plus 999, you know, 321, it's the same set of numbers. I think that's pretty obvious. But also, what do you notice when if you added these? What's 1 plus 1,000,000? Well, that's 1,000,001. What's 2 plus 999,999? That's also 1,000,001. In fact, every one of these pairs is going to be 1,000,001. Huh. How interesting. So by adding the same set of numbers in reverse order, little Carl Friedrich noticed that I'm going to get 1,000,001 exactly how many times, folks? Exactly how many times am I going to get 1,000,001?
A million.
1,000,000 times. So that means my final answer is going to be 1,000,000 times 1,000,001. Well, not exactly. Why is that not exactly going to be my final answer? Because I counted it twice, didn't I? Did everybody catch that? That I just did. I added to 1,000,000.
Then you divide by
Why?
2.
And this presents a very, very powerful formula. This is actually what is called an arithmetic series. For those of you who remember that term, that's not so much important as the fact that we can get a formula. Where did the 1,000,001 come from? Well, that was the first and last term added together. 1,000,000, there was 1,000,000 terms. So I'm going to present some very cool and clean formulas for you. The first formula is as follows. I want the sum from I equal 1 to n of the number 1. Well, what does that mean? I'm going to add 1 plus 1 plus 1 plus 1 plus 1 exactly n times. Anybody want to make a guess what that is? 1 plus 1 plus 1 plus 1, because there's no I here, so it's just going to stay 1 until I'm done. I'm going to add up the number 1
Infinity?
n times. So it's what? N. Now we're going to do what we just did. I equal 1 to n of I. This is 1 plus 2 plus 3 plus 4 plus 5, because I is incrementing. 1, 2, 3, 4, 5, 6, all the way up to n. We just developed a formula. It's right here. It's going to be n plus 1 over 2. That's the formula that's credited to Gauss. Now, again, I love the story. If there's any truth to it, that's nice. It doesn't have to be true. Legends don't have to be true. They present a point. A great amount of our historical lore is not necessarily based on fact, but it makes for a good story. So I love the Gauss story. Again, it doesn't matter if it's true or not. I tend to believe that he might have been obnoxious as a kid, but I think genius would be a better description. Now, there are a few more that are useful. I'm not going to derive these. In my discrete math class, Math 245, it's a proof-oriented class, and they do a lot of different types of proofs, proof by induction being one of the more commons. So the next ones are actually proof by induction is how you would actually do them. So what if I wanted to do I squared? I want to do I squared. Well, that's n plus 1, 2n plus 1 over 6. We are not going to prove that. We're going to demonstrate it in a moment. And the only other one we ever actually use for our purposes is the sum of the first n cubes. And it turns out that's just the square of this one. That's n squared, n plus 1 squared over 4. How these are derived in the first place is kind of complicated. Proving they're true is actually not very difficult. So let's just take some simple numbers. Let's just say we want to add the first 5 of each of these. So in the first case, I want to go 1 to 5 of the number 1. That's 1 plus 1 plus 1 plus 1 plus 1. Well, duh, that's 5. In the second, let's say we wanted to go 1 to 5 of I. Well, that's 1 plus 2 plus 3 plus 4 plus 5, which would be 15. But according to the formula, what should it be? According to the formula, it should be 5 times 6 over 2. Good. I do get my 15. How about the next one? Well, the next one, if I said, let's add up the first 5 positive squares, I get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. That's 1 plus 4 plus 9 plus 16 plus 25. That's 55. Let's put the numbers in. If n is 5, this says that should be 5 times 6 times 11 all over 6, and that is 55. Life is good. Now let's add up the first 5 perfect cubes. All I'm doing now, I'm just verifying that the formulas are correct, and I'm showing you how you would do that. And I picked small numbers, 5. I don't need to verify it with 5,000. So here, that would be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. So 1 plus 8 plus 27 plus 64 plus 125. And what's that? 9, 36, 100. That'd be 225. All right. According to the formula, it should be 5 squared times 6 squared over 4. Well, let's see. That's 900 over 4. Yep. Now, these are what we're going to use next today. Okay, these 4 summation formulas. And the way we're going to do them is we're actually going to estimate areas under curves using these. It sounds kind of crazy. It is kind of crazy. All right. So let's do the following. And by the way, I do have posted notes on all of this stuff, because I'm assuming this is unexplored territory for most everybody. What we're doing right now, this is not calculus. This is a stepping stone to get us to a place. Now, imagine, if you will, just in general, so here's how we're starting the day. I want to find the area under the curve. Now, whenever you hear the expression area under the curve, that always means the area from the curve down to the x-axis. Okay. Now, where that can be a little confusing, then if my curve is below the x-axis, that would actually give us a negative number, because I'm always measuring it from curve to the x-axis. So if I'm under the axis, or if half my curve was below the axis, you would actually get canceling. So area under the curve always just means from curve to axis. So what I want to do is I want to create what's called a partition. Okay, a partition, think of it like walls. So if you're in a building or you're in a house, you get all of these walls separating rooms. Those are called partitions. I want to partition this into n rectangles of equal width. Okay, so just sort of imagine, okay, I'm going to keep splitting it in half. I'm going to just keep going, whatever n is. I'm going to have n rectangle, or excuse me, I should say n partitions of equal width, or n sections, however you want it. N is finite. There will be a limit at some point. And then what I'm going to do is take the right endpoint and make a rectangle. So that would be the right endpoint. So I'm going to make a rectangle by going straight across. And notice that some of my rectangles go outside, some of my rectangles stay completely inside. Now, here's the most important part of all of this is if I said find the area of the rectangles, the geometric regions, base times height, that would be a really, really good estimator for the area under the curve. It can't equal the area under the curve unless I somehow got so lucky that my little bit of overage on these was exactly the same as my little bit of underage on these. No, that's not going to happen. But the area of my rectangles is a really good estimator for the area under the curve. Does anybody want to guess, how would I make it a better estimator? I only drew 8 rectangles. How would I make it a better estimator?
Make smaller rectangles?
Yeah, more rectangles. Or in some cases, more cowbell. I don't know, one or the other. I want more rectangles. Oh, I made 8 rectangles. What if I made 8,000 rectangles that are really skinny? Then would you agree the over under would be tiny? So you guys can sense there's a limit somewhere in the process. Yes, the area will become equal when I take a limit, but this is a good starting point. So what we're going to do here is we're going to figure out how to make a summation out of this. All right. So first of all, we'll call this x0, and this will be x1, and that'll be x2, all the way down, and this will be the last one will be xn. If n were 8, if n were 8,000, and n is however many rectangles I have, that's what n is. Okay, so that's the first rectangle, the second rectangle, the third rectangle, that's the nth rectangle. In fact, in general, we'll call this one here xi minus 1, and this we'll call xi. Think of dot, 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 you know, along the way. So what is delta x1? Delta x1 would be x1 minus x0. That's exactly what it means to be a delta x. What's delta x2? Well, that'd be x2 minus x1. And in general, delta xi would be xi minus xi minus 1. Okay, kind of see the pattern here. So the ith delta x is how we'd say this. Now, in my particular picture, notice all of my delta x's are the same width. A little later, we're going to look at what happens if they're not all the same width. So right now, all the delta x's are the same. So right now, every single delta x is exactly the same. And how big is my delta x? Well, let me make it really simple. Let's say that this was 1 and this was, 51. I went from 1 to 51. So that would mean I have a width of 50. And I have exactly 10 rectangles. If I had a width of 50 and exactly 10 rectangles, then exactly how wide is each rectangle? 50 over 10. Okay. My width right now is what? It's b minus a. That's how wide this interval is. And exactly how many rectangles do I have? N. That's a scalar. That's a constant. These are not variables. A is that x coordinate, B is that x coordinate, and n is the number of rectangles I have. These are all just simple constants that you would have. So this is the width of every single interval. Okay. And there's a little bit of algebra going on here, but that's pretty trivial stuff. Now, I want to go back and describe all of my x's in terms of this. So that would mean that x1, which is, x1 clearly is equal to x0 plus delta x. Okay, so in this case, that would be what? A plus b minus a over n. So then what would x2 be? Well, x2 would be x0 plus 2 delta x's, which would be a plus 2 of these. I'm going to write it on the other side. I'm going to write b minus a and then times 2. Dot, dot, dot. What would xi be? Because that's actually what we want. We want to be able to describe it in general. Well, that clearly is going to be just a plus b minus a over n times I. All right. Sorry, make that a little more readable here. So if I asked you what is each coordinate, and by the way, let's make sure this is consistent. What would xn be? Xn would be a plus b minus a over n times n. And if you look, n's would cancel, and I'd have a plus b minus a, which is exactly b. And that's what it's supposed to be. That's a good thing, by the way. Now, I have just figured out a way to write all of these without ever using an x. Why? Because I now need to describe the heights. So I want to find this area. We'll call the first rectangle area 1. We'll call the second rectangle area 2, and so on. So good pen here. Area 1 would be, what's the height? Remember the height, I was using x1 for the height. So area 1 would be f of x1 times delta x1, which of course would just be this. Area 2 would be f of x2 times delta x2, and so on. The ith area would be f of xi times delta xi. Now, the nice thing in this example, all the delta x's are exactly the same. In general, they're not necessarily, but in this case, they are. Now, what I need to do is figure out a way to just do this, because I said I don't want to use x's. So I will use this. So now I'm going to go ahead and erase this. I can say then that ai is f of xi, this, f of a plus b minus a over n times I, that looks kind of crazy, times delta x, so times b minus a over n. Now, as crazy as that looks, a, b, and n are constants. I just means I was on the first one, then the second one, then the third one, then the fourth one, and so on. So now the final statement I'm going to make in this case is that the overall area, this is where we use a squiggle, it's being estimated by, it is not equal. It is estimated by the sum from I equal 1 to n of my a's. In other words, it's a1 plus a2 plus a3 all the way up to an. That's a reasonable estimator of my area. I will get an equal as the delta x is all, they approach 0. That's where the equal is going to be. I'm going to take a limit at some point, just not yet. Okay. And what I would do is then obviously replace this with this. Now, all of this is really nice and exciting and new and everything, but how do I actually do a calculation? Well, as a general rule, there are very few functions that I could actually pull this off and calculate. So what we do is we generally will use functions that are simple polynomials, because those are the only ones that will give us formulas that we can actually do. So that's what I'm going to do next. We're going to do a simple, fairly simple problem. All right. So here's our goal. I'm going to come back to all this. Again, I've got some posted notes. They look kind of scary at first until you realize, oh my gosh, I'm just doing algebra. So we want to find the area under the curve. So the area under, how about f of x equals, I'll keep it a simple, let's see. Let's do a parabola. How about 3x squared plus 2 over the interval, let's say 1 to 4. So what does that mean? Well, first thing is, I'm going to give you a rough sketch of this. Don't worry about scale. That's really not that important. So when x is 0, I'm at 2, and this is going to rise very rapidly. And I want the area under the curve from 1, let's say that's 4. So I want this area right here. Well, that's a curve. So I can't just use geometry and break it up. So we're going to do what we just did a moment ago, but now I've given you a specific function. So creating the sum will actually be much easier this time. So the first thing I'm going to do is split this into n rectangles of equal width. Okay, pretend that these are equal width and actually pretend they're straight. So I'm going to do this. All right, I know those are kind of sad looking rectangles. They're kind of supposed to be straight across. I'll do better. Let's see. There we go. You kind of get the point here. There we go. That's much better. All right. I want to find the area of each of these rectangles. And again, we used the right endpoint. So let's say that one right there is the ith rectangle. So what I need to do, if I can describe that particular area, then I can create my summation and life is good. So right off the bat, what is our delta x? In this case, all of the delta, I'll write delta xi, but they're all going to be the same. all of my delta x's are going to be exactly the same. Yes, delta xi is the xi coordinate minus the xi minus 1 coordinate. But because all of these are equal widths, all I need is the length of the interval divided by the number of rectangles, which was n. So this will simply be 4 minus 1 over n. Oh, okay, that made it easy. Now, x0 is 1. So in general, what is xi? Well, just a minute ago, we said xi was my starting point, a, in this case, a would be 1, plus exactly I multiples of delta x. That's what we just did. So this would be 1 plus delta x times I. And that would be 1 plus 3 over n times I. See, that doesn't look as scary now when I don't have all the a's and b's. Again, that's a, that's b. So b minus a is the width over n. So for my starting point, if I said what's x1, you'd say my starting point plus 1 delta x. If I said what's x5, you'd say my starting point plus 5 delta x's. So what's xi? My starting point plus I delta x's. Now the next thing is I need f of xi. So what is f of xi? Well, I'm going to put that into there. That's going to be 3 times 1 plus 3 over n times I squared plus 2. Okay. So all I did was insert that in there. Now let's clean that up a little bit. So if I multiply this out, 1 squared is 1. 1 times 3 plus 2, that'd be 5. I'm going to have 6ni in the middle times 3, so that'd be 18. Oh, sorry, over n times I. And then when I square that, I'm going to have 9 over n squared times I squared times 3. So plus 27 over n squared times I squared. The reason I'm kind of doing all of that at once is I need the space. You know, off to the side, go ahead and multiply that out, distribute the 3, add the 2. Take as many steps as necessary, but this is what I get. So then what is the ith area? The ith area, this exact area is going to be this, this times this. So this is f of xi times delta xi, which is this times this. Now, when I multiply out that stuff, what does that give me? That will give me 15 over n plus 54 over n squared times I plus 81 over n squared, n cubed times I squared. That's the area of this. Oh, and that would be for any n. So if I said 4 rectangles, if I said 4,000 rectangles, that's what n would be. N would be the number of rectangles. So finally, I can say that area, which is estimation of this, well, let me just throw those guys in there. Okay, whatever that is, that's my estimation of the area. And in the end, by the way, I'm going to take a limit. I'm going to take a limit as n goes to infinity, because if n goes to infinity, that means that each of my delta x's is getting smaller and smaller and smaller. So taking the limit as delta x goes to 0 or taking the limit as n goes to infinity will serve the same purpose. Because as n grows without bound, each of these is approaching 0 then. Now, I just need to calculate this. Well, how the heck am I supposed to do this? Well, n is a constant. And didn't we just prove a moment ago that the summation of a sum is the sum of the individual summations? So we just proved a little while ago that I can first do this. And then secondly, I can factor. What do you mean factor? Well, I is the index. I is the only thing that's changing in the summation. I can't go anywhere. But n is a constant. 81 over n cubed is a constant. I can factor it out. Meaning this is equal to 15 over n times the sum from I equal 1 to n of the number 1. We have a formula for that. This would be 54 over n squared of I. We have a formula for that. And this would be 81 over n cubed I squared. We have a formula for that. Now I can use the summation formulas I presented earlier. So I am going to now do the unthinkable. I'm going to erase this because I'm not going to have enough room to finish this problem. I'll leave the original instruction up there. All right, so how do I do this? Well, let's do the first one. So I'm going to bring this up. Well, didn't we say the sum from I equal 1 to n of the number 1 would just be n? I'm adding 1 plus 1 plus 1 n times. Oh, well, that's kind of nice. Plus 54 over n squared times what? Well, let's see. We have a summation formula for that. That's Gauss's formula. That's n plus 1 over 2. Okay. And then this guy here, that was n plus 1, 2n plus 1 over 6. This right here, this quantity is our estimation of the area under the curve for any value of n. Remember, n is the number of rectangles, so n would have to be a positive integer. There's not really, decimal n's or negative n's. Now, this right now is not an integer, but I can simplify this tremendously. And I want to simplify it first because ultimately I want to take a limit. So clearly that's 15. How about over here? Well, I can cancel one of the n's. I can cancel the 2 and the 54. So right now I'm at what? 27 n plus 1 over n. I'll leave it like that for just a moment. How about over here? I can cancel one of the n's. I can cancel a 3. And right now I'd have 27 n plus 1, 2n plus 1, all over 2. Well, that's still not beautiful, but it's, oh, I'm sorry, 2n squared. Sorry, lost my n squared there. Now, here I'm going to show you a cool little, not a trick, a technique. Make sure you're muted, please. A lot of background noise. It's probably you, Nate, usually is. n plus 1 over n. Can I write that as 1 plus 1 over n? Yeah. So I'm going to rewrite this as 27 times 1 plus 1 over n. Okay. Over here, I've got n plus 1 times 2n plus 1, and I just want the n squared part. I don't need this anymore here. Could I first write this as n plus 1 over n times 2n plus 1 over n? I think I can. And then let me do the same thing. Then wouldn't that be 1 plus 1 over n times 2 plus 1 over n? Ah. And I had a 27 halves. Sorry if this looks a little cramped. All right. This is the estimation of my final answer. What I have right there is the estimation of my final answer. How do I get the actual area? I'm going to take a limit. We said area was estimated by this. Area will equal I'm going to write it two ways. Because our formula had delta x equal b minus a over n, having delta x go to 0 or n go to infinity, because n was in the denominator, served the same purpose. Okay. This is an estimation because I had a finite number of rectangles. This would be equal because my rectangles, their widths approach 0, and the number of rectangles approaches infinity. This will be exactly the area, which means I want to take the limit of this. Part of the reason I rewrote it in this form is because it makes the limit now ridiculously simple to take. You see, as n goes to infinity, what are those guys called again? You guys remember the term? We haven't used it in a couple of weeks. What are they called?
Asymptotes? No.
Transient terms.
Transient terms. Those are transient terms. They each approach 0. Why is that important? Because that means that what's left, my answer is going to be just 15 plus 27 times 1 plus 27 halves times 1 times 2. What's that? 15 plus 27 plus 27. The area under my curve is exactly 69. Now, this was long. This was tedious. This is a stepping stone, like I said, to get us to where we need to be, because ultimately finding area under the curve involves clearly a limit. Now, if my curve was geometric in nature, in other words, if I was actually finding the area of, let's say, a triangle or a trapezoid or a rectangle, that's easy. Oh my God, we learned that as little children. If I said, let's find the area of a circle, that's easy. But I've got a curve. It's not a fixed geometric shape that I'm aware of, and I'm trying to find the area under that curve. Well, the way we do it, first of all, is by making rectangles and then taking a limit and then going from there. This only worked. This process I did only worked because I chose a function that was a simple polynomial. Had that function had an e to the x or a sine x or something, I wouldn't have been able to do this, because in creating the original formula, I wouldn't have been able to get these beautiful summation formulas. They would not have shown up in the same way. They only showed up when I have sum of I or sum of I squared or sum of I cubed, not the sum of cosine of I or the sum of e to the I. No, they won't show up there. So now we have to step back and say, okay, this worked and I see the answer, but it can be more complicated than this. So now I want to do the next level. I love this problem because you can find it for any polynomial boundaries. You can find it using these limits, but it won't work for a transcendental function. It won't work for anything trig or inverse trig or log or exponential. Okay, so let's go now. We're going to do now level 2. Okay, same problem as before, but now I'm going to change it up on you. I want to partition this, but just like anything else, I want to partition this, but I don't want to be bound by any set of rules, meaning I don't want one partition to have any effect on another partition. So everybody here, as I'm giving you this huge plot of land, everybody mark your own territory. So maybe there's my first one, and maybe there's my second one, and maybe there's my third one, and maybe, there's my next one, and maybe there's my next one. So maybe this is my partition. I'd say my partition looks somewhat random. In fact, let me throw one more in there. I'll throw that one there. There we go. Now it's perfect. Now, before we said we were always going to take the right endpoint, and there's a reason we took the right endpoint. It made it really easy to describe the height. I don't want to take the right endpoint. I want to pick the height for this interval right here. I can pick the left endpoint, the right endpoint, the midpoint, 3/7 of the way. I want you to pick a height that's completely random in the interval. Let's say I pick the height to be right there. Now, this one I decided to actually use the left endpoint, and this one I decided to use close to the midpoint. This one I decided to use, let's say about 24% of the way over. In other words, I'm being completely random here. And here, let's say I decided to use the midpoint-ish, and here maybe 2/3 of the way over, I don't know. And then over here, maybe I did about right there. I'm going to be completely random in my choices of where in the interval to choose the height. In the previous example, we could only use the right endpoint. We used the right endpoint and went across. So that meant the first rectangle, the height was f of x1. The second rectangle, the height was f of x2, and so on. Now we're just being random, totally random, because this is actually the most general way of doing this. So like before, let's say this is xi minus 1, and this is xi, making this the ith rectangle. And in fact, this spot that we chose right here, let's call that w sub I, where w is somewhere between xi minus 1 and xi. So the spot I chose in the first rectangle, we'll call that w1. And the spot I chose in the second rectangle, we'll call that w2, and so on. So the height of the first rectangle is f of w1. The height of the second rectangle is f of w2, and so on, where the w just has to be somewhere between the endpoints. Okay, so now, oh my gosh, this is craziness. But now I've got it so that the ith area is f of w sub I, this is my ith rectangle, times delta xi. Remember, where w is a number between them, and w could be any real number between them. Yikes. So now I can say once again, my area is estimated by this. And by the way, in this case, the x's, I would say, range from A to B. That at some point I need to state that. Now, this here looks totally random, but here's what's crazy. In the previous example, when we chose the right endpoint and squared it over, we got a reasonable estimator and we got an equals when we took the limit. If I just said randomly choose widths and randomly within each rectangle pick the height, it turns out this would actually be closer. In fact, I could get lucky and hit the area exactly on the nose. I'm not really looking for that, but the sense of randomness here actually allows us to explain this much better. Now, here's the problem though. I want to take the limit as the delta x's go to 0, or as n goes to infinity, however you want to look at it. But the problem with that is, if I said, well, let's take this rectangle and let's just make it smaller and smaller and smaller. Let's just keep subdividing it, but not touch any of the other rectangles. Well, that won't work. I need all of the rectangles to get smaller. So mathematically, how do we say that? So I'm going to introduce some notation that looks completely whacked at first, but it's very, very formal and very important notation. So first of all, this is a partition, right? The vertical bars, that is my partition. The widest such thing, okay, P is the partition. This symbol right here translates as the norm of the partition. Okay, two bars around the P. Now, if anybody here has ever worked with vectors, if you've ever worked with vectors, what do the vertical bars around a vector always mean? Does anybody know? If you've ever worked with vectors, you know, in a trig or pre-calc class, you put vertical bars around a vector. What does it mean?
The modulus, like
another word, magnitude. That means the length of the vector, means the magnitude. Vertical bars always mean, in this, the two vertical bars always mean magnitude. So in this case, magnitude would refer to a width. When we get into Calc 3, magnitudes can be areas, magnitudes can be volumes, because we're working in multiple dimensions. But on a number line, a magnitude would only be a length unit, right? Because I'm on the number line there. So the norm of the partition simply means the largest width, the biggest magnitude. That's all, that's it. So we use this crazy notation to indicate the biggest magnitude. So when I say area equals, then we're going to say I'm going to take the limit of this, but I'm not going to say as delta x goes to 0. I'm going to say as the norm of the partition goes to 0, as the largest magnitude goes to 0. Now here's my way of explaining that, because I've got n rectangles and I want them all to be going to 0 at the same time. How do you do that? I mean, how do you even say that? Okay, so here's how it works. And some of you unfortunately might be scarred for life after this example because it's utterly terrifying. Okay. I'm trying to join the evil league of geniuses, okay? And every evil genius, of course, has a few things in common. First of all, they have their evil lair. I have an evil lair. I live there. And then they have their evil weapon of mass destruction. So I chose my weapon of mass destruction to be a shrink ray. So I carry this gigantic shrink ray around with me. And what I do is I come to class and I look for the biggest person in class. So I think, William, that's probably you. So what I'm going to do is point my shrink ray at you and go, pew, and now you're 1 point. I've shrunk you to 1 point, which means you are no longer the biggest person in class. There is now a new biggest person in class. Maybe it's Jeremy. So now I pointed Jeremy. Pew. Eventually, even the smallest person in class will eventually be the biggest person in class because I've shrunk everyone else down to 1 point. So what I'm going to do is take the largest person in class and shrink them down to 1 point with my shrink ray. By the way, it is reversible, just so you know. I think I just have to sprinkle water on you or something, then you come back. So I go to each person in the class and I shrink you down to 1 point. Eventually, every single person in the class will have been shrunk to 1 point, but I start with the biggest and work my way down. I'm giving you an absolute description of what's happening here. I start with the largest rectangle and I have its width approach 0. So there's now a new largest rectangle. So its width is now going to approach 0. Now there's a new largest rectangle. The norm of the partition approaches 0 means if the biggest one is approaching 0, then everyone smaller than that will eventually approach 0 because they will eventually be the biggest ones. And this is the way of having every one of these eventually, okay, my shrink ray. So this here is the area under the curve. This is called, some of you may have heard this term before, a Riemann sum. Now, Riemann sums are extremely important. We use this all the way through Calc 3 every time we set up a problem to find areas or volumes or surface areas or anything where we're going to use an integral to do a calculation, an actual geometric calculation, we use Riemann sums. Now, we're never going to physically calculate this, strangely enough. We're going to translate this. But once I get this set up, I'm going to now translate it into something. And that's the next thing. The Riemann sum, put up here now. Okay, for this problem that I've done, the limit as the norm of the partition approaches 0 of the sum from I equal 1 to n of f of wi, where w was between, right? That's the definition of wi, delta xi, and what this is important, that x stayed between a and b. This is defined to be 3 bars. We haven't used that in a while. This is defined to be, not calculated to be. This looks familiar, except I have numbers here. This is called a definite integral. What we have been doing are called indefinite integrals. We have been doing integrals of functions, and our answer is the antiderivative. Our answer is the function whose derivative gave us the original integrand. And that's the most important part of the process, being able to integrate or find the antiderivative. This is called a definite integral. The answer here is a scalar. This is not a function, it's a number. In this case, it's equal to the area under the curve. Now, how do we actually calculate that? Well, if I don't have the a and b, then I know that's just a function. It's the antiderivative. So where does the a and b come in? That gives us a value. The antiderivative has got to figure into this somewhere. Yeah, it does. So if you look on your schedule, next day, we do something called the Fundamental Theorem of Calculus, which is widely regarded as maybe the single most important piece of work in human history. I don't know. Maybe, well, what about Einstein's theory of relativity? No, can't have theory of relativity without this. Every result that has happened in the last 400 years in math and science stems from the Fundamental Theorem of Calculus. And we're going to be proving that next day. The proof itself is a little bit challenging, but it's the results that we really need to know. Now, that allows us to use integrals to answer questions down the road. So we don't have the means of answering the question yet. We will soon enough. So this is equal to the area. So the first and foremost thing I want you to see is once I'm able to state the Riemann sum, I can say it equals the definite integral. We're not going to calculate this. We're going to calculate this. So in the problem that we did earlier, we found the area under the curve. I believe we did 3x squared plus 2. I think that's what we did. And the interval we did was 1 to 4. If I wanted to now state this as a Riemann sum, then the Riemann sum would look like this. The limit as the norm of the partition approaches 0 of the sum from I equal 1 to n, f of wi. So I would write 3, oops, that's a lousy w, 3 wi squared plus 2 delta xi, x between 1 and 4. Now, sorry, this is a little too cramped. I'll write it over here. Now, we're not going to calculate this. We're going to translate this into the definite integral from 1 to 4 of 3x squared plus 2 dx. And we know that equaled 69 because we already calculated it. What we don't know right now is how to actually physically calculate this. We will, and you're going to love it because it's not hard. But that requires next day's class. So we go from the statement of the problem to the Riemann sum, from the Riemann sum to the definite integral. And then we're going to learn later how to calculate the definite integral. And that's basically the rest of this course is all in calculating definite integrals and all the different ways of doing things and all the different applications. So now what can I do with the definite integral? I mean, are there some rules? Before we even learn how to calculate it, let's discuss some of the rules. All right, so let me start with a really simple problem. I can always keep it simple. So if that's A and that's B, let's call this y equals f of x. And if I asked you for the area under the curve, you can now tell me that the area under the curve is the definite integral from a to b of f of x dx. We don't know how to calculate it yet. That's not even important. I just want to be able to state it. So we all agree that's the area under the curve, hopefully. Now, there's some really simple algebraic things that I can do with this. First thing. Let's call this A1 and let's call this region A2. Do you think it's safe to say that my overall area equals A1 plus A2? Everybody okay with that? Just yell out yes or no. You think that's okay?
Yes.
Yeah. Let's state A1 and A2 as definite integrals then. Well, A1 then should be A to C of f of x dx. And then A2 should be C to B of f of x dx. That seems reasonable. Okay, so if I said the integral from A to C of f of x dx plus the integral from C to B, that's the same as just going A to B. So in other words, it's kind of like saying I went from A to C, stopped, picked it up right where I left off, continued, that gave us this. That hopefully makes perfect sense to you. So I have something like this. I have the integral from -5 to 7 of f of x dx. And I want to add to that the integral from 7 to 12 of f of x dx. Can I write this as one integral? Anybody, can I write this as one integral?
Yeah, -5 to 12.
-5 to 12 of f of x dx, exactly. That's all I wanted you to see from this example. Oh, okay. As long as I'm ending where I started, life is good. Now there's a few little pieces that we can mess with. All right, so the next thing, we have this picture, everything makes hopefully perfect sense. What if anybody want to try this one?
F prime of x plus c.
Going from a to a of f of x dx. Same f of x, I'm going from a to a.
Is that just a
One
regular integral?
So same thing we just did, except before I
A
said
to A.
a to b. Now I'm saying a to a.
So it is from A to A.
So you might want to try to tell me, can I do anything with that? A to C, A to B, I want you to go A to A.
0,
0. Why would it be 0?
because you're not moving anywhere.
Look, oh yeah, I
there's
basically
no-
am asking you the area of the line segment, aren't I? Does everybody
There's
see
no
that?
slope.
Ah, no.
Oh, so
Slope
you-
does not figure in an slope never figures into an antiderivative ever the rest of your life. There is no such thing as slope in an antiderivative. Slope only applies to derivative. I just asked you to take the area of something with 0 width. Oh, okay. That's what I wanted you to see. Now, by the way, this is an important result. What do you think about this one? I know A to B is the area under the curve. I want you to go B to
Can that
A.
be negative?
Negative what? How about negative of the original? Do you agree with that? Oh, and why? Because I'm moving backwards. It's as if all of my delta x's, if you will, are now negative. So everybody cool with that? If I reverse the order of these are called the limits of integration, by the way. And so terrible use of the word limits because you're not taking a limit. But the outer limits of my region, if you will, the extremities of my region, those are called the limits of integration. I reverse the order of the limits. That will change the sign of the integral because it's as if I'm moving backwards. It's as if all of my widths are technically negative. Remember I said if the curve is below the axis, then basically it's like saying you have negative heights. An integral can be negative. An integral can be 0. Okay, there's no rules on a value. Now, if I said I want you to set up the problem to find an area, well, then you should get a positive number. But an integral itself can be positive, negative, or 0. Now, this last one's kind of tricky. So now I'm going to make up a new picture. Totally new picture. Okay. And this will be the last of this piece of the puzzle. All right, I now want to picture okay. Clearly, my overall area is the integral from A to C of f of x dx. I think we all agree with that. Okay. And now I want B to be somewhere in between. I'm changing the rules. Before I had A to B and C was somewhere in between. Now I want A to C with B somewhere in between. And I'm going to show you something really cool about the results. All right, just like before, let's call that A1 and let's call that A2. And I think we all agree that A to C of f of x dx is equal to A to B of f of x dx plus B to C of f of x dx. Agreed? I want this by itself. So can I say a to b of f of x dx equals a to c of f of x dx minus this? Everybody okay with that? I want to get this area by itself. So I just said it's the big area minus this area. But just for fun, we just did the negative of the integral a moment ago. I'm going to move it up. I'm going to move it up here so you can see it. We just said, well, if I reverse the order of the limits, that changes the sign. So can I take this quantity right here and rewrite it as a to c of f of x dx plus what? Plus
C to B.
c to b of f of x dx. And by the way, it's still equal to this. Hey, wait a minute. A to c, c to b, a to b. Even though, wait a minute, even though b's on the inside. When I first did the example, I said a to b, we'll put c in the middle. So then going a to c and c to b gave us a to b. Now I put b in the middle. I made b smaller than c. And you know what? Isn't that the exact same formula we came up with before? Yeah. I'm proving to you that it doesn't even matter the order of the numbers. If I go from a to c, c to b, that's the same as going a to b. Regardless of what the numbers are. It doesn't matter what order the numbers are. Whoa. Let me do an example. I've got the integral from 2 to 10 of f of x dx, and I want to subtract the integral from, how about 7 to 2 of f of x dx. I would really like to write this as one integral. Well, we don't have a formula for integral subtraction. We only have a formula for integral addition. So can I rewrite this as 2 to 10 plus what? Okay, mute yourself, guys. It sounds like somebody's flushing a toilet.
10 to 7?
From 10 to 7, is this a good thing? Yeah, so this will equal what? 2 to 7. It's basically a way of combining integrations. By the way, the most important part of this is I have to have the same integrand. I can't be switching f of x and g of x. No, 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 no. I have this, okay? And I want to combine them and write them as one integral. But there might be situations in the future, there will be, trust me, many situations, where I actually want to go the other way. I have something and I want to pull it apart. So in other words, I can go in either direction. It doesn't matter. So now today, we did not get into how to calculate a definite integral. No, we got into how to write one and how to translate. Next day, we're going to talk about how to calculate it. Again, that's called the Fundamental Theorem. And that one, it's a little bit of a challenge, but once we get it, it's a tool that you will now have forever and ever and ever. I mean, everything math and calculus related comes from that. Everything in physics comes from that. There's so many applications, and it's just not that complicated. We're just not ready to all do it all at one time, right? So